Hello everyone, it's Miss Stover again. Today we're going to be talking a little bit more about atomic structure, in particular talking about this concept of an isotope. So to talk about that concept, we first have to talk about the man who discovered the concept of an isotope. That was Frederick Soddy. He actually proposed the idea of isotopes in 1912. And he said that isotopes were atoms of the same element having different masses due to varying numbers of neutrons. He actually won a Nobel Prize in Chemistry in 1921 for this work with isotopes and radioactive materials. He was probably one of the men that was responsible for the Manhattan Project and some of the discoveries that went along with that. We'll be getting more into the history of the atom a little bit later on, but you do need to know that Frederick Soddy was the first guy who proposed this idea of isotopes, and it wasn't proposed until 1912. So, what is an isotope? Well, we've been kind of looking at that a little bit and trying to figure out what an isotope was. So we can see that we see the word here, isotope. Well, guess what? An isotope is another fancy name for an atom. Okay, another fancy name for an atom. But it's specific about the kind of atom. So you'll notice we have hydrogen, hydrogen, and hydrogen. They're also given other names: protium, deuterium, and tritium. And we'll talk more about what those names are in just a second. I think you can kind of get it from there. But notice here, look at the number of protons. 1, 1, 1. Well, we know that has to be the same because the atomic number for hydrogen is always 1. That means for an atom to be hydrogen, you have to have protons of 1. So then electrons also have to be 1 because we have atoms. We do not have anything but atoms. But you'll notice, look at here. Look at what starts happening to the neutrons. So the difference in these particular atoms of hydrogen is not their numbers of protons because they are the same, not their numbers of electrons because they are the same, but their numbers of neutrons are different. So if we look a little bit more at the nucleus, we can see the nucleus of this protium, hydrogen 1, only has a single proton. There's nothing else in there, just a proton. Then we look at the deuterium, hydrogen 2, and we notice that we have this yellow proton, but we also have this orange guy, this neutron as well. Then we see into tritium, we see the yellow proton, one yellow proton for each, but then we see 2 of the neutrons here. So you can see pro is a term that means 1, Dew means 2, and tri means 3. So in actuality, the other names that are used for these hydrogen isotopes also give you a clue to the mass numbers of them. So we come to find out that isotopes are atoms of exactly the same element because they have the same number of protons. But they have different mass numbers. And the reason that they have different mass numbers is because they have different numbers of neutrons. So that is what distinguishes an isotope from one another. So isotopes, though, don't occur as single atoms. They actually occur as mixtures of isotopes. So all elements actually occur like this. Very rarely do we find any particular atom out there by itself. If we have a sample of an element, it's a sample that contains multiple atoms of that sample. So we call that a mixture of isotopes. Now you're going to say, but Ms. Stover, elements aren't mixtures. No, they're not. But what we're trying to get at here is that we do not contain particles that are exactly the same. We contain particles that are different because they have different numbers of neutrons. So we get this idea that elements, even though they're pure substances, sort of have this quality of a mixture because they do not have atoms that are exactly alike. And we'll find out more about that and when we talk about the history of the atom in a little while. So we also see that isotopes are atoms of the same element that differ in the number of neutrons. So just another way to give us the same definition that we've already talked about, that isotopes are the same as the other elements, as the other atoms, because they have the same protons, but they differ in numbers of neutrons, and that's their difference. So we can see that if we have hydrogen, if we have a sample of hydrogen, you are not going to have only this. This is the most common isotope of hydrogen because we know our periodic table says that hydrogen has an atomic mass of 1.008. So 1 would be the closest number. But when we have hydrogen, what we get is we get some of this, and some of this. But because we have this mass, we know that we get more of this than we do these other two. These other two are much more rare. Same with helium. Helium has an atomic mass of about 4. Okay? What we know is that we could have helium-3 and helium-4. Well, because the mass of helium is right around 4, we know that helium-3 is very rare. We get more of this, but in any helium, we get both of these. We do not just see one of them. We get a sample that has both of them. Lithium is the same way. Lithium has a mass of 5.98. We can see that that's closest to lithium-6. Well, that doesn't mean that all the lithium atoms are out there that are lithium-6. What we have is we have a mixture of lithium-6 and lithium-7 so that my mass comes out, my average mass comes out to be closer to lithium-6 than lithium-7. So we can kind of see this idea of this mixture of isotopes. Now, don't get me wrong. That doesn't mean that elements are mixtures. What it means is we're talking about the particles. The particles that we see in these elements are not identical. They are actually mixtures of the same element because they have the same number of protons. You'll see in every single case. In hydrogen, we see 1, 1, 1. In helium, we see 2 and 2. Over here, we see 1, 2, 3. 1, 2, 3. So you notice they have to be the same atom because they have the same number of protons, but we can see the thing that changes is the neutrons. So, naming isotopes. Well, clearly, we're going to name isotopes, and we've already been doing that. We've already been talking about that, but we want to talk about some isotope pairs here in just a second. So we can do one of two things. We can put the mass number after the name of the element, so this is one way that we do it, and we've already been doing this. And the other way we can do it is to use the complete symbol. Both of those are going to identify the mass number. And the mass number is what's going to tell us about the number of neutrons. So if we look, we can see we have carbon 12 or 12,6C, which tells you the same thing. These are both the same atoms. Then we can have this other carbon called carbon 14. Well, you can see over here carbon 14 says 14,6C. Well, these two atoms are isotopes of one another. Why? Because they have the same number of protons, but because they have different mass numbers, that means they have different numbers of neutrons. Okay, another example, uranium-235 and uranium-238. What we see very clearly, they're both uranium. They both have 92 protons. But uranium-235 has 3 fewer neutrons than uranium-238. So we can clearly see what's going on here. This one has 146 neutrons, and this one has 143 neutrons. So they differ by the number of neutrons that they have. Let me put that down there so that you can see that. And that's the end of our discussion today about neutrons.